Okay, let's go ahead and start. If I could have everyone's attention, please. I want to make one quick announcement, and that is I wanted to remind everybody that there are bonus points for completing the surveys. So if you guys remember at the beginning of the quarter, I said that there was one during the second week of class, and I hope that you completed the survey for the 9th week of class. And the last part that you need to complete to earn those bonus points is to complete the teaching evaluations as well. Okay, so you got to complete 3 surveys. All right, and if you complete all 3, then you will get the bonus points. So please take the time to complete it. And I would appreciate it if you would comment on the online homework. And if you've used Sapling before and you're using Wiley Plus or vice versa, if you could comment on both, that would be great. All right? All right, so if you guys remember, last time we started looking at what we call the integrated rate law. Okay? As we will see later on, it's important for us to figure out the rate law that corresponds to a reaction. We will see later on that we can use that to obtain information about the pathway. All right? But before we start looking at pathways, we want to understand what it means when we say the rate law of a reaction. And we said the only way you can establish the rate law is to carry out the experiment and either look at rate versus concentration or look at concentration versus time. All right? And we said that even though we looked at how we can use the rate of a reaction and the concentration of the reactant to figure out the rate law or the order of the reaction. But we said, unfortunately, actually executing that in the laboratory becomes hard because measuring rate accurately or precisely sometimes is difficult. And so we have a different approach where we look at concentration versus time, and we derive a mathematical equation that describes the concentration versus time dependence. And last time, we derived the expression for the first order reaction. So if you have just one reactant, and for a first order reaction, we said the general form of the reaction turns out to be ln A minus ln A0 equals minus KT. And so if we rearrange that equation into a form that gives us y equals mx plus c, we can see that we end up with a straight line with a negative slope. So if you plot the natural log of the concentration of your reactant as a function of time, and you have a straight line which is with a negative slope, it means that that reactant is first order. Okay? So what you would do is, so this is much easier to do in the lab because essentially what you do is at different time intervals, you measure the concentrations of A. Now, remember, the concentration of A is the amount unreacted. All right, so as the reaction progresses, the concentration of A is the amount that's left unreacted. Okay? And so different time intervals, you can measure the concentration of A. At the beginning, when t equals 0, it will be A0, and then you just measure the concentration at different times. And now, you take the natural log of A, and if you make a graph, and if the graph comes out to be a straight line with a negative slope, then you know it's first order. All right? If you don't end up with a straight line graph with a negative slope, it means it's not first order. All right? If your points are scattered, or if it looks something different, then you know that it's not first order. Okay? Now, having said that, now we're going to define a new term that we're going to look at. And this term is called half-life. So the half-life is the time it takes for the concentration of a reactant A to fall to half its original value. Okay? So if I were just to plot, instead of plotting natural log, if I were to just plot the concentration of A as a function of time, all right? And so if this was the initial concentration, then we know that it decays like that. So instead of plotting natural log A versus time, if you just plot concentration versus time, this is what it would look like, the plot, okay? Now half-life is the time it takes for the original concentration to be halved. So it's exactly half of this, and if it's exactly half of that, this would be half of the original concentration, and we call that, the time it takes is called T half, T subscript half to indicate the half-life. So the half-life is the time it takes for the original concentration to be halved, okay? Now if I take this concentration, which is half the amount, and look at the time it takes for it to be halved, that would be, now the concentration would be a quarter of what you started with, and this would be 2 T halves, where this is 1 T half, and then this is the other T half, and so T half plus T half gives you 2 T halves, okay? Now if you want to take the quarter amount, and the time it takes for the quarter amount to become 1/8 would be that, and that is 3 half-lives, or 3 T halves, and that becomes A0 over 8. And so this would be the third. The time will be the same, okay? My plot looks like this is a little bit longer, but in reality, if it is 2 days for the first half-life, it'll take another 2 days for the second half-life. So the second half-life would be 4 days, and then the third half-life would be 6 days. Do you understand that? So it's the time it takes for the original concentration to be halved, all right? And we call that half-life. So if we want to derive an equation for half-life, we can say at half-life, we know that the concentration of A is half the original concentration, and now T becomes T half, because we call that, the time it takes for that is half-life, and we call that T half. So if we go back to the original equation that we derived for the first order reaction, we know ln A over A0 equals minus KT, and we know at half-life this becomes ln A is now equal to this, and that will be over A0 equals minus KT half, where T is now half-life. So essentially what I'm doing is I'm replacing this term with that, and this will become the half-life. Okay? You can see that the original concentrations will cancel out. Therefore, ln 1/2 equals minus KT half. Now, since there's a negative sign here, and to get rid of that negative sign, I'm going to take the inverse of that. So if I take ln half, mathematically it's the same as negative ln 2 equals KT half. All right? And so now I'm going to rearrange that and get a term for T half, which is the half-life. And so if I rearrange that equation, I can say T half, there's a negative sign there as well. So the two negative signs will get rid of each other. T half equals ln 2 over the rate constant K. ln 2 is 0.6931 divided by K. So the half-life is 0.6931 divided by the rate constant. Now that's worth remembering. So if you want to calculate, if it's a first order reaction, it has one reactant, and you want to calculate what is the half-life. And remember, what is the definition of half-life? It's the time it takes for the original concentration that you started with to be halved. Okay? So let's apply this in a problem. So if you turn to this problem, okay, so if I may turn to that. So here is an example of applying what we just learned in a problem. What is the rate constant K for the first order decomposition of N2O5 at 25 degrees Celsius if the half-life of N2O5 at that temperature is given? Okay? So what they tell us is that it is first order. So it's important to check that. What is the order? Remember, so far we derived an expression only for first order. So this is a first order reaction. And we know that the half-life for this is T half equals 4.03 times 10 to the 4 seconds. They want to know what is the rate constant for that reaction. All right? So I know that the only relationship between these two that we've looked at thus far is that T half equals 0.6931 divided by K. I know what this is. This is a number. This is what I need to find. So you can see K equals 0.6931 over T half. And therefore K equals 0.6931 divided by the half-life, which is 4.03 times 10 to the power 4 seconds. And so if you put that in your calculator and work that out, it comes out to be 1.72 times 10 to the negative 5. And you can see that the unit is per second. Remember, K is rate constant, and the unit for rate constant varies depending on what the order of that reaction is. So this is first order, and you can see that's the unit for the rate constant. So that's pretty straightforward. Now, having calculated that, now for the second part, they tell us under these same conditions, what percent of N2O5 molecules will not have reacted after 1 day. All right? So what they're asking is, when T is 1 day, they want to know what is the percent unreacted. So we want to figure out percent unreacted. Okay? So if we want to calculate the percent unreacted, now we have to make use of our integrated rate law. And we know the integrated rate law is ln A divided by A0 equals minus KT. All right? From the first part, we calculated K. Time is 1 day. They want us to calculate percent unreacted. Can everybody see? This would give me the ratio of unreacted. Remember, A is always the amount unreacted. And since that's the amount unreacted, if I wanted to calculate percent, remember, what does percent mean? The amount unreacted divided by what you started with, or the total, which is the original concentration, times what? It's a percent times 100. Do you see that? So if I just find the ratio and multiply it by 100, that will give me the percent unreacted. All right? So what we're going to do is we're going to figure out what this ratio is. So we can say ln A over A0, which is the original concentration, or in this case, I should put the actual numbers, which is ln N2O5, and the original concentration of N2O5 equals minus, now I know my K is 1.72 times 10 to the negative 5 per second, and times time. Now remember, in kinetics, what is the unit that we use for time? Seconds. So they give us 1 day, so that means I need to convert that to seconds. So you know that there are 24 hours in a day, and 60 minutes in an hour, and 60 seconds in a minute. All right? So hours and hours will cancel out, minutes and minutes will cancel out. This is per second, and second will cancel out, so it becomes a unitless quantity. And so I know that ln N2O5 over the original concentration of N2O5 equals, if you figure that term out, it comes to 1.49. Okay? 3 sig figs, 24 hours is an exact number, 60 minutes is an exact number, 60 seconds is an exact number, so we end up with a number that is 3 significant figures. All right? Now what I'm going to do is take the inverse log to get rid of this log. So if I take the inverse log on this side, I need to take the inverse log on that side. So what I end up with is N2O5 divided by the original concentration of N2O5. And if I take the inverse log of that, that comes out to 0.23. Now remember, I'm taking the inverse log, so if I'm keeping track of sig figs, I have a 3 sig fig number. When I go from here to here, I only count the decimals, so it goes to 2 significant figures. All right? And then now that I have figured this out, now percent unreacted would be N2O5 divided by N2O5, the original concentration, times 100, which is 23%. All right, so all I've done is just taken the value that I calculated and multiplied by 100, and that gives me a percent. So that means in one day, 23% is left unreacted. Now, when you're solving a problem, you have to read the question carefully, because if they asked you for percent reacted, the percent that actually reacted is 77%. So when you're carrying out online homework, sometimes it'll ask you to calculate the percent unreacted. Sometimes it'll ask you to calculate the percent reacted. And so if 23% is unreacted, you know that 77% has reacted. Is that clear to everybody? Okay. So that was a look at a first order reaction. Okay? Now we need to do the same thing that we've done for the first order, and we want to look at what happens with a second order reaction. So we're going to derive an expression for the second order reaction. And so if you have a case where you have just one reactant, and if it is second order, we know that the general form of the rate law would be rate equals rate constant times the concentration of A. Now it is second order, it is raised to the power 2. All right? I hope you took time to review the stuff that we covered last Friday, because this is going to build on what we've looked at. Okay? So all of you know this is the general form of the rate law. We know it's second order, and we know that rate equals K times A to the power 2. But since we want to derive an integrated rate law, we're going to replace this rate law, the rate term, with change in concentration, incremental change in concentration of A as a function of incremental change in time. And we put a negative sign in front because it's a reactant, and a reactant is consumed in that reaction. Okay? So this equals Ka squared. All right? Now I'm going to put all the concentration terms on one side and take everything else to the other side. And so if I keep the negative sign here, I can say this over A squared equals K times dt. All right? Now if I integrate this over the range of initial concentrations, the limits are initial concentration to any concentration A, and over here, that would be at time 0 to any time t. If you integrate that, what you end up with is 1 over A minus 1 over the initial concentration equals Kt. So if it's a second order reaction, and the integrated rate law, or the dependence of concentration on time, comes out to be in this form. Okay? So you need to know this equation. I won't give you these equations, so you need to know whether it's a first order, what the equation should be. You need to know what the equation would be for a second order reaction. Okay? Now, if I want to rearrange this so that I get it in the form of y equals mx plus c, in other words, to figure out whether it's going to, what form of this equation will give me a straight line graph, I can say now that 1 over A equals Kt plus 1 over A0. So I'm just going to take this term over there. So now this will turn out to be the y-axis. Now you can see that k is the slope, time is the x-axis, plus c gives me the intercept. So now if you look at k, you can see that it's positive, and so this gives me a positive slope. All right? So the general form of this if I take this and if I plot a graph of 1 over a versus time, this is the y-axis, time is the x-axis, you can see I end up with a straight line graph. All right? So if I were to plot this, I would end up with a slope, and the slope will give me the rate constant, and everybody can see that this is a slope that has a positive slope, and the intercept will be 1 over the initial concentration. So what this means is that if I were to carry out an experiment in the laboratory, and so if I were to look at different time intervals, I have different concentrations of A, and so when at time 0, this will be the initial concentration, and then let's say at 50-second increments, if I measure the concentration of A, all right? Now in your Excel spreadsheet, now you take the inverse of A, and you can put those values, all right? And if I plot 1 over A versus time, and if I end up with a straight line graph with a positive slope like that, then I know that that will be a second order. All right, so you're looking at the variation of concentration versus time, and so you're making a plot, and if you make a plot of 1 over A versus time, and you end up with a straight line with a positive slope, that means it's second order. If you don't get a straight line, but if you take these values and take ln A versus time and it gives you a straight line, what does that mean? First order. All right, do you see that? So you look at the shape, the form of the graph, and you can figure out which graph gives you a straight line, and that will tell you whether it's a first order reaction or a second order reaction. Okay? Now, we can do the same thing that we did for the first order, and we can start looking at half-life. So if I take half-life for a second order reaction, we know at half-life, we know that the concentration of A is half of the original concentration we started with, and we know the time is called T half. And so if I go to 1 over A minus 1 over A0 equals KT, and we know if I take this equation that I started with at half-life, now this A, I'm going to replace this A with that term, so what I'll have is 2 over A0 minus 1 over A0 equals KT half. All right, so all I've done is taken the equation that we derived and replaced it with these terms because we're looking at half-life. And you can see that if I subtract this from that, what I end up with is 1 over A0 equals KT half. And therefore, KT half, sorry, we want T half. So T half equals 1 over K times the original concentration. So the equation that you would use if you wanted to calculate the half-life for a second order reaction is 1 over K times the original. All right, so these are just derivations. Okay, so what I need you to do is at home go through the derivations and make sure you know the appropriate equation for first order, the appropriate equation for second order. All right, now let's work a problem where we apply this. So if we turn to the next problem, now we're looking at the application of what we just learned. And so the decomposition of C2H6 to methyl radicals is second order. So that's your key. You're told that it's a second order reaction. Okay? If the second order in the reactant and second order overall. There's only one reactant, so you know that it will be overall second order as well. Okay? The rate constant is given. If the initial concentration is this, what is the concentration after 205 seconds? So let's just write down everything that's given to us. We know that the rate constant is 0.0448 liters per mole per second. We know that the initial concentration of C2H6 is 0.0100 moles per liter. We know that the time is 205 seconds. And they want us to calculate what is the amount unreacted at that point. Okay? What is the concentration after 205 seconds? So what is the amount of the reactant that's left over after 205 seconds? So what I want you to keep in mind is there are only two equations that we've learned for second order reactions. One is for half-life. They don't mention half-life at all. So we know that if I want to figure out this, the equation that I'm going to use is 1 over C2H6 minus the initial concentration equals KT. All right? Can everybody see this is what I need to find? I know this. They're giving us the original concentration. They're giving us what K is. They're giving us what time is. So this is just knowing the appropriate equation and applying it. So I'm going to put the unknown on one side and take everything else to the other side. So this would be 1 over C2H6 equals KT plus the original concentration. K is 0.0448 liters per mole per second times the time is 205 seconds. So this and this will cancel out, plus 1 over 0.0100 moles per liter. Okay? Can you see that this moles and that moles will cancel out, and this liter and that liter will cancel out because this is the inverse of the inverse. Okay? So, sorry, they do not cancel out. This will remain moles per liter, at liter per moles, and this becomes liter per mole as well. So let me just put this number. If you take this and multiply this by this, it's a 3 sig fig number, and that number comes out to be 9.18 liters per mole, plus this is the inverse of moles per liter. So if you take that, this becomes 100 liters per mole as well. The reason the units don't cancel out is because we're not multiplying, we're adding them. And you can only add apples to apples. Can you see that? You have the unit is liters per mole. The unit for the other is the inverse of moles per liter, and therefore it's liters per mole, and therefore you can add apples to apples. Does that make sense to everybody? And so you know that you're on the right track, because if you end up with two different units, you know you can't add the two numbers together. All right? So now that we know that we have the same units and you can add apples to apples, now I know that 1 over C2H6 equals that. And if I add these two together, now keeping track of sig figs, this is a 3 sig fig number, this is a 3 sig fig number. Now I'm adding these two numbers together. When you're adding numbers, what do you keep track of in terms of significant figures? Decimals. So can you see that 100 has 0 decimals? So when I add these two together, I'm going to give it to the least number of decimals, which is 109 liters per mole. I'm going to take the inverse because I want to calculate the concentration. So if I take the inverse of that, this comes out to be 9.17 times 10 to the negative 3. Now the inverse of liters per mole becomes moles per liter. And I know that I end up with the right unit, and therefore you know that you haven't made any careless mistakes along the way, because I'm calculating concentration and I end up with the appropriate unit. All right? So in all of these problems, I want to remind you that keeping the unit there is helpful, because it sort of is checking to make sure that you're doing the problem correctly. Because if you end up with the right unit, then you know that mathematically you've set up your equations correctly. All right? So if you end up with the right unit, you know for sure that you haven't made any careless mistakes along the way. Okay, so now we've looked at first order, we've looked at second order, now we're going to look at zero order. These are the common ones, okay? So if we take a zero order reaction, then we're going to do the same thing that we've been doing all along, okay? So if I take a zero order reaction, can everybody see that rate equals K, A raised to the power what? If it's a zero order reaction, it should be raised to the power what? 0. Anything raised to the power 0 is what? 1, okay? So that means rate equals K. Now, now I need to derive the integrated rate law, so I'm going to look at small incremental changes of concentrations of A as a function of time, giving me K. Now I'm going to rearrange this equation so that I put all the concentration terms on one side and everything else on the other. So this would be concentration of A. On this side, I will put negative K, changing time, incremental changes in time. So if I integrate this over the range of the initial concentration to any concentration A, and that corresponds to t equals 0 to any time t. And if you integrate that, the outcome comes out to be concentration of A minus the initial concentration equals minus kT. So if it is a zero order reaction, then the equation that describes the dependence of concentration versus time is given by this equation. So this is called the integrated rate law. And if I want to look at the form of a straight line graph, I can rearrange this and say concentration A equals minus kT plus A0. This would be the y-axis. Now, can everybody see this is m, but this is a negative slope. So I'm going to put the negative sign in front of this to remind me that it has a negative slope, okay? And this is y equals mx plus c. So this would be kt, like that. So now if you look at this, this is a graph that has a negative slope. So if I plot this, my y-axis will be concentration of A. I'm plotting it versus time. This will give me a straight line graph like that, where the intercept is the initial concentration, and the slope of this graph will give me the rate constant K, and this is a negative slope, okay? So the rate constant, when you take the slope, the rate constant has no sign. Remember we talked about the fact that rates don't have sign, and neither do rate constants, all right? But I want you to pay attention to, if you end up with a negative slope, then you know it's a zero order reaction, all right? And so if it's a zero order reaction, if you take different times, different concentrations of A, when it's 0, this will be the initial concentration. Now at different time intervals, I said 50-second increments, you measure the concentration of A that's unreacted. And now if I plot A versus time, if I take this data and plot it, and now if I end up with a graph that gives me a straight line with a negative slope, it tells me that it is zero order, all right? And so what we generally do in the lab is, now that we've looked at all three, the way you figure out the order of the reaction is that once you've got this, so essentially in the lab, what you do is, like, I'm just going to repeat that again. So you have time, and so 0, you measure the concentration of A that's left unreacted. At time 0, that will be the initial concentration. And then at 50-second increments, for example, you can measure the corresponding concentrations. Now you'll make a third column where you'll figure out the natural log A. And then you have another column where you'll have 1 over A. All right? And what you would do is that you would make 3 graphs. All right? You make a graph of time t versus A, or A versus T. This is the y-axis. ln A versus T, and 1 over A versus T. And so it's like this. So let's say you're carrying this out in the laboratory, and essentially what you do is once you complete the experiment, you draw 3 graphs. All right? And so you make 3 graphs, and only one of these will give you a straight line. So if you look at this graph, this is 1 over A. Remember, 1 over A versus time is what? Second order. Does that give you a straight line? No. And if 1 over A versus time, it has to be a straight line with a positive slope. We don't get a straight line with a positive. So we know we can rule out second order. Now look at the second plot. It's ln A versus time. ln A versus time gives you a straight line with a negative slope. And you can actually measure the slope, which is negative 1.3 times 10 to the negative 3. All right? So because that gives you a straight line, what does that tell you about this reaction? That is first order. And I can actually, from the slope, I know the rate constant is, you toss out the negative sign, the rate constant is 1.3 times 10 to the negative 3. Got it? And then if you take A versus, I don't get a straight line. So it only has to be one of the 3. Do you guys get it? And so you make 3 graphs, and from that, you can figure out what the order of the reaction is. So that's what, I hope you carried out this in the laboratory, and you can figure out the order of the reaction based on drawing the 3 plots. Yes?
This is only for one reactant.
There's only one reactant, all right? And it can only be one of the 3. Do you understand that? So you're only going to end up with one straight line graph, all right? And so that would be the one that tells you the order of the reaction, okay? Now, I also want to derive the half-life for a zero-order reaction. So for a zero-order reaction, if I want to derive the half-life, we know that at half-life, we know that the concentration of A equals half the original concentration. We know that time now becomes half-life, okay? So we go to the equation for zero order, which is 1 over A minus 1 over A0 equals negative KT. We know at half-life, we're going to replace all of this. Now this becomes 2 over A0. Wait a minute. Sorry. I'm doing the second order one. Please bear with me. I'm thinking about something else. So we know that at half-life, concentration of A is A0 divided by 2, and we know T equals T half. And we know for a zero-order reaction, we know this is concentration of A minus A0 equals negative KT. That's the one for zero order. Previously, I wrote it for the second order, okay? And so if I take this, and now I'm going to say at half-life, I'm going to replace the terms. I know that A equals A0 divided by 2 minus A0 equals minus KT half. Okay, so now we're looking at half-life. And you can see that if this is 1, this is half. If I subtract one from the other, what I'll end up with is negative A0 divided by 2 equals negative KT half. So the negative signs will cancel out on each side. And so T half equals the initial concentration divided by 2K. All right, so the integrated rate law, because you have to derive this mathematically, we only look at the 3 common orders. The common ones are 0, first order, and second order. All right, and so we derive the rate laws for the 3. Now, on the class website, when you're studying at home, I want you to kind of summarize everything this way. So there's a copy of this on the class website. And so what we're looking at is, we looked at 0, first, second order. All right? The rate law would be for 0 order, rate equals K. For first order, rate equals K A raised to the power 1. Rate equals K A raised to the power 2 for second order. Okay? Now the form of the integrated rate law that we derived is given here. So A equals minus KT plus A0. ln A equals minus KT plus ln A0, or 1 over A equals KT plus 1 over A0. So this is the form of the integrated rate law that we derived. Okay? Now the plot needed to get a straight line, because remember, we're going to determine whether a reaction is first order, second order, or 0 order based on which plot gives you a straight line. So for 0 order, A versus T will give you a straight line with a negative slope. Okay, so the slope will be negative K. Here, ln A, for first order, ln A versus T will give you a straight line graph with a negative slope. And 1 over A versus T will give you a positive slope for a second order reaction. So that's why we draw 3 graphs and figure out which one of these will give us a straight line. Okay? Lastly, the half-life equations that we derived is given here. So half-life for 0 order is this, half-life for this is this, and half-life for second order is that. Okay? You need to remember these equations, all right? And if you worked enough examples, like the homework as well as the online homework will give you enough practice so that now you should be able to know which equation to use to figure out the half-life for 0 order, half-life for second order, and half-life for first order. Is that clear? To begin with, keep this handy with you. Just paste it on the wall, and as you're carrying out homework, just go to that table and you can look at the appropriate equations. And after a while, you'll be so comfortable with it that you no longer need that table. All right? Now, the problem is that up to this point, what we've looked at is only one reactant. All right? And if it's only one reactant, then it's pretty straightforward. How do you figure out the order when you have more than one reactant? All right? So if you turn to the next page, we have to come up with something more clever to figure out the integrated rate laws if you have more than one reactant. All right? Now, if you guys remember, previously when we looked at rate versus concentration, remember we said we designed the experiment so that we can cancel out one reactant. Remember when we worked at problems last Friday, we said if you want to figure out what the order of the reaction is, we actually designed the experiment so that we keep the concentrations, we measure rate at different concentrations. But if you have more than one reactant, you always keep the concentrations of one of those reactants the same so that they cancel out and change only the other. All right? Likewise, if we want to use the integrated rate law, we have to design our experiments in a special way. All right? So far we have considered the integrated rate laws for simple reactions with only one reactant. It turns out special approaches are required to deal with more complicated reactions. All right? So let's say we are looking at this. Okay? So if I want to write the rate law, so we're looking at now 2 reactants, and if I want to figure this out, the rate law, as all of you can see, rate equals K, concentration A, let's say raised to the power M, times concentration of B raised to the power N. Okay? So now we have to design this in a special way so that we can look at the rate law of one at a time. And the way we do that is we set up the concentrations so that one concentration is really small. This is of the order of 10 to the negative 3. The other is 1 molar. So can you see that the difference between the two reactants is about 1,000-fold? All right? So we specially designed the experiment so that the concentration of one reactant is kept really small, like of the order of 10 to the negative 3, and the other is of the order 1,000 times more, like 1 molar. And the reason is that when the reaction takes place, the smaller concentration is going to be the limiting reactant. All right? And so what's going to happen is the smaller one is only going to react, and relative to the smaller concentration, the bigger concentration doesn't appear to change. Because remember, the limiting reactant is 1,000 times more dilute. So the reaction will take place at the scale of 10 to the negative 3, and the 1 molar, which is 1,000 times more concentrated, stays relatively unchanged for the scale of the reaction. Can everybody see that? And so what happens is that we set it up so that we take A is the one with the smaller concentration, B is the one with the larger concentration. So B concentration is much, much greater than A. Now what happens is, because this is much, much greater, it appears relatively unchanged. And so what happens is, as the reaction progresses, the concentration of B does not change all that much. So we're going to approximate it and say that as the reaction progresses, the concentration of B will always be the original concentration, which is a constant. All right? So if you go to the rate law, where we say rate equals K, A raised to the power M, B raised to the power N, we can say now we can replace the concentration of B with the original concentration of B. And can everybody see that this term does not change? So this is a constant. All right? So because this is a constant, I'm going to include this with the constant, and I come up with K prime, which this is called the pseudo rate constant. Okay, it's not the real rate constant, but because this includes the pseudo rate constant, which is K prime, is actually the real rate constant, which is this K times this constant, which is the concentration of B. Do you guys see that? So essentially what I'm doing is, by keeping one concentration really large, I'm making it look like you have only one reactant. All right? Because one concentration does not change. And now what I would do is I would carry out this experiment, and I would take, at different time intervals, I will look at concentration of A. B does not change, it's a constant. So at t equals 0, this will be A0, and I'll measure the concentrations. All right? Now I will take ln A, and I'll also plot 1 over A. And in this way, I will see whether I end up, which of these will give me a straight line graph. So if this is experiment A, over here, this is experiment A, and you can see now which line gives you a straight line, ln A. If it's ln A versus time in straight line, what does that tell me? It's first order in A, all right? And the slope that I calculate, this is where you want to watch out. The slope, so let's say that if I plot this out, and I end up with ln A versus time will give me a negative slope. Okay, so these are the points on that graph. Now the slope gives me K prime, which is the pseudo rate constant. All right, because we've reduced this to look as if you have only one reactant. All right, the rate constant is the pseudo rate constant, which is K prime. Got it? So now I have to repeat this experiment and do this all over again. But now I have to keep the A concentration 1 molar, and I'm going to reverse the thing. Now I'm going to make B the one that is smaller in concentration. All right? So now you can see the A concentration is far greater than B, and therefore now the one that will be constant will be this. So now you can see that this term is constant. All right? So now this equation reduces to rate equals K double prime. This is a different one. All right? K double prime times B raised to the power n. And so now once again I have to repeat this experiment where I have T, and then now I'm looking at concentration of B, so that this will be 0. This will be the initial concentration of B to begin with. At different time increments, I will measure the different concentrations of B0. Now I will have to look at ln B versus 1 over B. And so you have to do 2 experiments. And so now if you turn to experiment B, now I want to look at this. This is B versus time. Is that a straight line? No. This is 1 over B versus time. Is that a straight line? No. But if I take ln B versus time, it gives me a straight line with a negative slope. So what is the order with respect to B? First order. All right? So now from this plot, and now this slope that I get, so once again, it just so happens that you have ln B versus time gives you a straight line. And so these points would be what you would figure out. And now you can see this slope will give me K double prime. All right? And we know that that is first order as well. But I'm not interested in the pseudo rate constant. I'm not interested in K prime, neither am I interested in K double prime. What do I need to figure out? K. So now that I've figured out its first order, I can go pick any one of these slopes, and I know that K prime equals the real rate constant times B, original concentration of B raised to the power 1. Do you guys get that? I know this number I have got from the plot. This is the original concentration, which is 1 molar. I've already figured out its first order. All right? So now I can rearrange that and find out what the real rate constant for that reaction. K equals K prime over the initial concentration over the raised to the power 1 because it's first order. Does that make sense to everybody? You can use the same equation for K double prime and you should end up with the same answer. It's 1 rate constant. You see that? You can use a K prime, the pseudo rate constant for experiment A, or you can use the pseudo rate constant for B. So just hold on. This is on the class website, all right, under your worksheets, all right? And you can see that these have 2 different slopes, but you will end up with the same rate constant, okay? We'll stop there for today.